Hello, and welcome to a digital differential equations lecture video for Salt Lake Community College. In this video, I'm going to continue looking at Chapter 2.4, Mixing Problems. Specifically, I want to look at an application problem that comes up in your homework. Two freshwater ponds are connected by a stream. Each contains 1,000 gallons of fresh water. An accident on the side of the road causes a spill of 25 pounds of chemical into the upper pond. Water flows into the upper pond at 4 gallons per minute, and then into the lower pond at 4 gallons per minute, and then out of the lower pond at 4 gallons per minute. So the volume of each pond stays constant. If it is known that fish can't live if the concentration is above 0.01 pounds per gallon, how long will it take for the water to be safe in both ponds? Now, I really like this example because it drives home a direct application of why we might want to understand these mixing problems. Let's see if we can draw a picture that will represent this scenario. And what I'm trying to imagine with this problem is two ponds that are connected together. So maybe here's a stream coming down and flows into a first pond. And then that first pond flows down into a second pond. And then there's a stream that flows out of that pond. So maybe we can label these as first or upper pond. This one could be our second or lower pond. And we're told that there's 1,000 gallons in each pond. Water flows into the upper pond at 4 gallons per minute. And then from there flows out and into the next pond at 4 gallons per minute, and then flows out at 4 gallons per minute, so that all of the ponds have a constant volume. Now, at some point during the day, there's an accident that causes a spill of 25 pounds of chemical into the upper pond. And it's only the upper pond, not both. So imagine an accident right here. Car driving down, a truck driving down the road, comes across, hits a tree, and then some kind of a chemical spills into the pond. Let's assume that there is going to be constant mixing of this chemical into the pond. So I hope this scenario makes sense. Our question is, how long will it take for the water to be safe in both ponds? Now, I think we should acknowledge that when the chemical goes into the first pond, it will slowly start to mix around, and then it'll eventually start to travel into the second pond. So what happens in the first pond, the upper one, directly affects the second pond. But what happens in the second pond does not affect the first one, since water flows in one direction. I'm thinking about this because I want to think about which order I should solve this problem. And I think what I would like to do is focus on the upper pond first. So let's start there. Let's let x of t be the amount of the chemical in the upper pond. And let's say it's measured in pounds. Okay. So our differential equation would look like dx dt equals. Now, if x is measured in pounds, again, what would be the units of dx dt? I think it would have to be pounds per minute. Okay. Now I'd like to pause for a moment to give you time to think about what this dE would look like. So if you can, please pause the video, take a moment to think about what would the differential equation dx dt look like for the upper pond. I'll see you back here in just a moment. Okay, I hope you paused the video and thought about what this differential equation would look like. And I hope you came up with something like this. Remember, this differential equation is always going to be the difference between the rate in and the rate out. And the way I view this problem is you had two freshwater ponds. So the water coming into the upper pond is going to be clean water. The accident is what caused the spill of a chemical. It's not flowing in at some constant rate. The accident caused it. So I'm going to say that the chemical, there is going to be 0 pounds per gallon flowing in. And the water is flowing in at 4 gallons per minute. If we're keeping track of units, notice that the units of gallons and gallons cancel, so that we will be ending up with units of pounds per minute like we expected. The right-hand side, the rate out. So the rate out should be the product of the concentration. So the concentration of the material coming out, we don't know that exactly because it's changing. But we can write it as x of t measured in pounds. And since the volume of the pond is staying constant, I can divide it by the 1,000 gallons. And it's flowing out of the first pond at a rate of 4 gallons per minute. So again, keeping track of units, we see that the units of gallons and gallons cancel. And so we are going to end up in units of pounds per minute like we expected. Now that I know that the units work out nicely, I'm going to stop writing the units and just write the differential equation. So here we're going to have x prime, dx dt, x prime. It's going to equal. Now the rate in. Since there's going to be 0 pounds per gallon coming in, it means the rate in is going to end up being 0. And then we'll have the rate out, which is going to be minus. I'm going to write this as 4 over 1,000 or 1 over 250 times x. I want to include the initial conditions. Now, this water was fresh water until the accident happened. And when the accident happened, it caused, at time 0, 25 pounds of this chemical to be deposited into the lake. So I'm going to say your initial conditions when the model started is going to be x of 0 is 25. Of course, after that point, it's going to start to decline. This is our IVP. Now, we've solved a fair number of differential equations up to this point, and so for this particular problem, I'm not going to show the algebraic solution to this differential equation. If we're thinking about form recognition, no. Remember that there's only one function whose derivative is a multiple of itself. This is going to allow me to skip some of the algebra and jump right to the solution. X of t is equal to c e to the negative 1/250th t. I hope this is a jump that we're feeling a little bit more comfortable making. However, because we knew the initial condition was 25, we should actually probably write the solution to the initial value problem and say x of t is 25 e to the negative 1/250th t. This is the solution to our initial value problem. Now, if we're imagining this scenario, that this 25 pounds of chemical is dumped into the pond all at once, but then fresh water is flowing into the pond, and then all of this mixture is flowing out of the pond, that this concentration, or the amount of chemical in this upper pond, is going to be getting diluted over time, and will be reducing. Eventually, it'll be clean. And that agrees with our solution to the IVP. Notice that with our solution, this decaying exponential function would start at 25, and as time goes on, this would reduce the amount of chemical in the pond. We are being asked to find when is it safe for the fish. So let's think about the fish now. We are told that it's unsafe at 0.01 pounds per gallon. But we made our model in terms of pounds. How many pounds is in there? So remember now, if we want to figure out the concentration, but in terms of pounds, let's multiply by 1,000 gallons. When multiplying by 1,000 gallons, notice that your units will cancel. And what we end up with is a measurement of how many pounds this 0.01 concentration is. So when you multiply 0.01 times 1,000, I think you should get 10 pounds. So we can say it's unsafe for the fish if there's 10 pounds or more in the pond. Now we started with 25, so we're asking when is this going to decline to the 10 pounds that we have that's safe for them. So we're trying to solve this problem. When is 25 e to the negative 1/250th t, when is this going to equal to 10 pounds? Now, if I'm going to solve this, we want to get t by itself, so you're probably going to divide both sides by 25. To obtain e to the negative 1/250th t equals what is 10 divided by 25? 10 divided by 25 is 0.4. Then we'll take the natural log of both sides of our equation. With the expectation that the natural log and the exponential on the left-hand side will cancel, leaving just negative 1/250th t equals the natural log of 0.4. Or t is equal to, well, to solve for t, I'm going to multiply both sides by 250, by negative 250. When you multiply by negative 250 on the left and negative 250 on the right, then the 250 will cancel. So I'm going to get negative 250 natural log of 0.4. And write this as a decimal. Negative 250 natural log of 0.4. And I get this to be about 229 minutes. I'm rounding to the nearest minute, of course. Now, if it feels weird to say 229 minutes, let's divide this by 60 and say it'll take about 3.8 hours. For the pond to be safe for the fish. Okay. Now let's think about the lower pond. It takes 3.8 hours for the upper pond to be safe. How long for the lower pond? So for the lower pond, let's proceed by first defining our variables. Let's let y of t be the amount of chemical measured in pounds in the lower pond. Now, y of t is the amount of chemical in pounds. Then let's write our differential equation for dy dt. And again, think about the units. If y is measured in pounds, then dy dt is going to be measured as pounds per minute. And it'll have to be the difference of your inflow and your outflow rates. And let's think about the rate in. Whatever's coming into the second pond came out of the first pond. But what's in the first pond is always changing. But notice that we found how it changes here. This is how the chemical in the first pond changes. That's how it is. It's x of t. So there's different ways you could write it, but I'm going to write this in steps just so you could follow my work. So it's going to be coming in at x of t measured in pounds. And the upper pond is always at 1,000 gallons, so its volume is 1,000 gallons. And it's coming into the second pond at 4 gallons per minute. So if we're keeping track of our units, the gallons and the gallons will cancel. So this will be measured as pounds per minute like we want. Now this is what's going on, remember, in the lower pond. It's coming into the lower pond. It's coming into the lower pond by this rate in. How is it leaving the lower pond? Well, it's leaving the pond because there's some chemical coming out. And it's coming out at some amount, y of t, measured in pounds. This is going to be the amount of the amount of chemical in the second pond. And since the volume stays constant at 1,000 gallons, this first fraction gives us the concentration of the second pond. Remember, we don't know what y of t is. It's going to be changing. And it's flowing out of the second pond at 4 gallons per minute. Again, if we're keeping track of our units, this is where gallons and gallons cancels. So it's flowing out at a rate of pounds per minute. At this point, I can identify all the units agree. And so if I write our differential equation, we can write this as y prime equals. Now our first rate in, if I simplify the 4 over the 1,000, I can write this as 1 2/50th x of t. The second pond, the rate out, I can again write this as 1 2/50ths, but this is going to be y of t. And I'd rather write this as a function of a single variable, or on the right hand side, rather than x of t and y of t. So now I'm going to grab our x of t from our previous solution. Remember, x of t, the amount of chemical in the first pond, is represented by 25 e to the negative 1 2/50th t. So let's plug that in for x of t, so that we can write y prime is 1 2/50th times 25 e to the negative 1 2/50th t minus 1 2/50th y of t. I'd like to simplify this a little bit. like the 1/250th times the 25. I think if I double check that, I think we should get 1/10. So that y prime is 1/10 e to the negative 1/250th t minus 1/250th, and I'm just going to write y now. I want to include our initial conditions, that the second pond didn't have the spill occur in it. The spill only happened in the first pond, which meant when this all started, the amount of chemical in the first pond or in the second pond was 0. This should be our initial value problem for the second pond. So our IVP for the lower pond. Now, there's a variety of ways you might be able to solve this, but I'm going to be using the integrating factor method. And so to use the integrating factor method, I want to write it in our standard form where all of the y's are on the left-hand side of the equation. So I'm going to write this as y prime, I think this would be plus 1/250th y equals 1/10 e to the negative 1/250th t. In this form, we can find our integrating factor. So remember now, your integrating factor is always going to be mu equals e raised to the integral of whatever p of t is. In this example, our p of t, the coefficient in front of y, is the 1/250th. So it's 1/250th dt, or e to the 1/250th t. Now, at this point, this problem should start to look pretty familiar to you. So I'd like you to pause the video and work the next couple of steps on your own. Get to the point where we're looking at least for the constant c, and then maybe unpause the video to check and make sure you're going in the right direction. I hope you'll do this. Continue multiplying by the integrating factor and then solve for y and find your constant of integration c. I'll see you in just a moment. Okay, let's see how you did. I hope you continued like I suggested and solved this for y using your integrating factor method. And what I hope you did is you multiplied by everything by your integrating factor. So 1/250th t everything on the left and everything on the right. And I notice I just made a sign error. Our integrating factor is positive 1/250th, but I wrote negative on my exponents. I got to fix that. Now on the right-hand side, be cautious. On the right-hand side, there is your original right-hand side, which was negative 1/250th t, but our integrating factor has a positive 1/250th t. So this is what it looks like when we multiply by our integrating factor. And it should be that the left-hand side can be rewritten as an application of the product rule. So I hope you did that and wrote it as y times e to the 1/250th t prime. On the right-hand side, notice that you're multiplying two exponential expressions that have a common base. And so you would add your exponents to get e to the 0t. Of course, e to the 0t is just 1, so maybe I shouldn't even write this e to the 0t. Let's just leave it as 1/10. Now, double check and make sure that your left-hand side works out as an application of the product rule. Remember, when you're taking the derivative of this product, the derivative of the first is this y prime times the second regular, plus the derivative of the second. The derivative of e to the 1/50th t is this e to the 1/50th t times, by the chain rule, this 1/250th times your first function. So we can verify your product rule works. I hope you now chose to integrate both sides with respect to t. Of course, on the left-hand side, the integral and the derivative will cancel, and you just have y times e to the 1/250th t. And on the right-hand side, the antiderivative of 1/10 is 1/10 t plus c. We wanted to solve for y, so now let's divide both sides by the e to the 1/250th t. And I'm thinking about how I want to divide the right-hand side. I'm actually thinking it'd be nicer, rather than dividing each fraction or each thing individually, I'm going to just divide the entire right-hand side. By e to the 1/250th. This is a little bit different than how I've done some of the problems in the past. I'm just kind of trying to anticipate what'll be the best form. Now, so what I get here is y of t. Of course, on the left-hand side, those e to the 1/250th cancel out. So we'll just have then 1/10 t plus c times, I'm going to get rid of this fraction and introduce a negative exponent, e to the negative 1/250th t. This, of course, is our general solution, but we want to find our initial condition, the solution to the IVP. So remember, with this IVP, at time 0, there was no chemical in the second pond. So y of 0 has to be 0. So y of 0 is going to be 1/10 times 0 plus c times e to the 0. And this all has to equal 0. If I try and simplify this, I think this tells us just c equals 0. Of course, that has to be because 1/10 times 0 is 0, and e to the 0 is 1, so this is just c times 1 equals 0. C has to be 0. With this value of our constant, our model for describing the amount of chemical in the second pond should look like y of t equals 1/10 t e to the negative 1/250th t. This would be our model for the lower pond. Now remember, our question was how much time to be safe for the fish, or to reduce, I can't spell reduce, R-E-D, to 10 pounds. In which case we'd be trying to solve this equation. When is 1/10 e to the t, oh, not e to the t, I'm getting things out of order here. It's 1/10 t e to the negative 1/250th t. We need this to be less than 10 pounds. Now I did say less because it started out, remember, as 0 pounds. There was no chemical in that second pond. Let's go back to our picture. Remember, there was no chemical in this lower pond. The accident happened at the upper pond. As after the spill occurred, this chemical started spreading into the upper pond and then started flowing into the lower pond. But initially, y of 0 was 0. Of course, then this chemical starts to build up into the second pond, and then it starts to flow out of the second pond. And I want to make sure that this is always less than 10 pounds. So I guess I could set it equal to 10, but I set it less than equal to 10 because I knew that it didn't start out above it. It started out below. So if we're thinking of this problem graphically, maybe we can put a little sketch here. That here's our time. I'll make this a little bit bigger since I have all this room here. Here's our time. And here's the chemical. And we know it has to stay below 10 pounds. So let's put 10 pounds here. This down here is, of course, the safe region. And we know also that we started with 0 pounds. So I want to figure out, when is this less than 10? Now, algebraically, we have a problem. Even if I were to set this equal to 10, to find out when it's equal to the unsafe level, this is not a problem we know how to solve. This is not solvable algebraically. There is no way to solve for t when t is both a factor here and part of the exponent. So we're going to have to resort to some other method for finding out if this is up or unsafe for our fish. So I'm going to use Desmos. You can use any graphing tool that you like, but if you could, go to the web and let's go to Desmos.com. Let me try and get this to fit in our window nicely. Okay. And let's put in the function that we're working on. Y equals 1/10. I'm going to put it in as a decimal. So 1/10 is 0.1 t e raised to the negative 1/250th t. Make sure I put that in the decimals correctly. You do notice it does start out at the 0 pounds here. But I'm not able to see the other half of our inequality that we were working on. Remember, we wanted this to be less than 10. So let's put in a second y equals 10. What we should observe is that, yeah, this is less than 10. And it looks like it's less than 10 for the first 15 minutes at least. But it's increasing, so I want to make sure that it never gets too dangerous. So I'm going to change our scale. If you click on the wrench icon up here, we can change our settings. And I'm not sure where to do this. This might take some playing. Right now, the x-axis goes up to 17. Maybe we should change this to 100. Notice at 100 minutes, it's still increasing and has not reached the 10-pound maximum yet. Let's go a little higher. Maybe we should go to 200. Notice it's still increasing. So maybe we should go a little higher. Maybe let's go to 400. Notice at 400 minutes, we start to see the amount of pollutant in the second pond already starting to decline. And notice it never actually reached the maximum or the limit of 10 pounds. This tells us, now I'm going to go back to our graph, that the amount of pollutant in our second tank looks something like this. The graph looks something like this. It was increasing, but at some point it started to decline and starts to look like this. And we expect it to probably approach 0 again. Graphically, we could even ask Desmos to find the maximum. If you hold your cursor near the maximum, it does find it and says the maximum was at 250 minutes and it was 9.19 pounds. Let's call it 9.2. So we can say at 250 minutes, this is when our chemical in the second pond was at the maximum, and this would have been 9.2 pounds of the chemical. Notice it was never unsafe for the fish. It never reached a point where the fish were in jeopardy. Okay, I hope this example was helpful and it gives you all the material you would have needed for your homework for chapter 2.4. I'm going to end this video now. I hope it was helpful and I'll see you next time.